Okay, so yeah, as you just heard, I will talk about computation for a bit, but I will try to say a few things about error correction, because that's really the topic of this work. So this is joint work with Sergei Bravi, David Cosset, and Marco Tomomicho. Okay, so let me first say what we mean by quantum advantage. So basically, you have to do 4 things at least. You have to first find a computational problem which you think you can solve. Ideally, that's one that we care about in the real world. But maybe that's another for another day. Then you should try to find a quantum algorithm that solves this, and at the same time you want to show that actually this problem is hard for classical devices of, say, similar size. That's the second step. Then you can start thinking about architectural constraints, how you can realize this in a given architecture, and finally you can start thinking about fault tolerance. Okay, so first I would like to review a result which basically was just mentioned. It sort of achieves these first 3 steps in this hierarchy, and it deals with constant depth classical versus quantum circuits. We can show that constant depth quantum circuits are strictly more powerful than constant depth classical circuits. And this proof also incorporates an architectural constraint. We can deal with just a 2D geometry here. So what do I mean by constant depth circuits? A constant depth classical circuit is just a concatenation of Boolean functions. Every such Boolean function is called a gate. The number of input bits is called the fan-in of the gate. And basically, we can talk about the depth of the circuit as the number of time steps you need to execute the circuit. And mostly we're interested in constant depth circuits where the depth is independent of the problem size, and the fan-in of these gates will be bounded, which is sort of the analog of quantum gates. And these circuits may also take additional random bits. Now for quantum circuits, I probably have to say even less. So this is just a standard quantum circuit. And the way we use it is we encode the problem in the computational basis on top of these input bits. So maybe additional ancilla qubits in the state 0. Then we apply these 1 and 2 qubit unitaries, and at the end we measure in the computational basis, obtaining the outcome. Okay. And again, we're interested in circuits that have constant depth, independent of the problem size. This is what we call shallow circuits. Okay, so now I can state these results. Basically, what we found is a computational problem, whose details don't matter here. The important point is this problem, we can solve it using a constant depth quantum circuit, an ideal constant depth quantum circuit with certainty. And this circuit is geometrically local in 2 dimensions. So that's one side. The other side is this classical depth lower bound. So we can show that you cannot solve this using a constant depth classical circuit. In fact, if you want to solve this with a probability that is higher than 7/8, then you need at least logarithmic depth. Yeah, so it's a separation between ideal constant depth quantum circuits and potentially, well, classical circuits with noise, or with errors. Okay, so what I would like to discuss today are 2 extensions of this result. The first question we ask is whether we can do this in a 1-dimensional geometry instead of a 2-dimensional geometry. Of course, that's easier experimentally. And the second question is more important, especially for this conference. We ask whether this advantage persists if the circuit is noisy. So can we even see an advantage in that case? And the answer to this question turns out to be positive in both cases. First, we can show that constant depth 1D local quantum circuits are more powerful than arbitrary constant depth classical circuits. And then we can also show that noisy constant depth circuits are more powerful than constant depth classical circuits. For this construction, we need a 3D architecture with local gates. So I will briefly discuss this first result because the second one relies on the first one. In fact, this result might be easier in practice, even though it doesn't have any fault tolerance properties, but it's a much simpler scenario. Okay, and then I would like to focus on the second part. Okay, so let me begin by defining a problem, and to save time, I will just give you the quantum solution to this problem. And then you will see that this circuit solves the problem. Okay, so here's a circuit. It takes classical inputs, it produces classical outputs. The gates here are classically controlled Clifford gates. You see the circuit has constant depth. That's 5 or something. And it's geometrically local in one dimension, meaning that you can arrange these qubits on a line, and every gate is between nearest or next to nearest neighbors. So this is certainly the type of circuits that we're interested in. The question is, what problem is solved by this circuit? Let me define a problem which we call the embedded 1D magic square problem. It's the following. So you're given an input alpha beta, and you're supposed to produce x, y, which appear with non-zero probability in the output distribution of this circuit. So that's a computational problem. And we have a solution. You can solve this problem with a constant depth 1D local quantum circuit, namely this one. Okay, so by definition, this is easy to solve using such a circuit. And the interesting part, of course, is that this same problem cannot be solved using a constant depth classical circuit. In fact, we can find a polynomial-sized subset of instances, such that if you can solve most of these classically using the classical circuit, then the circuit depth has to be growing logarithmically with the problem size. Okay, so I will not give you the full proof of this, but I will briefly give you the idea of where this comes from. So we start with a magic square game. So this is a Viper type non-locality game. Alice is asked to fill in a row of this table. Bob is asked to fill in a column. They answer with 1s and -1s. And the winning condition is that in the field where this row and column coincide, they have to produce the same output. And the parity of Alice's and Bob's outputs has to be even or odd, respectively. So we know that, of course, this is something that you cannot win classically without communication. So the winning probability is at most 8/9. That's the classical value of the game. On the other hand, if you have EPR pairs shared between Alice and Bob, then you can win with certainty. So what does this quantum strategy look like? You get these inputs, and you simply measure depending on the inputs according to this table. So basically what you're doing is you're measuring Pauli observables. So you can rewrite this as a circuit. Then you have classically controlled gates, Clifford gates, which rotate to the right basis. So that's actually part of our circuit in some sense. But this problem itself is not hard enough for constant depth classical circuits because they can signal to some extent. So we can make it harder by stretching it out on a line. Okay, so we start with 2n EPR pairs. Now we get these inputs at the ends. We do entanglement swapping measurements in between. And basically this creates long-range entanglement, some Bell state up to a Pauli correction, depending on these measurement outcomes. And you simply measure using the previous measurements from the magic square game. And you can show that this is now hard or some variation of this problem. Okay, so let me now get to the second part. And here I would like to discuss fault tolerance. And the first thing I have to do is I have to tell you what our noise model is. And luckily to this audience, I don't have to explain why Pauli noise is natural. I hope you can accept this. So we consider a noise model, of course, where every operation can be noisy in the circuit. And usually we model this by introducing Krauss operators of errors. And now we're going to assume that these are Pauli errors with some distribution. Okay? So I have to specify the distribution, and here it's natural to assume that high-rate errors are exponentially suppressed simply because physical processes are typically local. So we want some notion, some description of distributions of random Paulis that has this property, and the description should be as general as possible. Now it turns out there's a very nice notion that formalizes this, and this is the notion of local stochastic noise that was previously used by Gottesman and also in this paper that we will hear about on Thursday. So this formalizes this notion that the errors are exponentially, high-weight errors are exponentially suppressed. So you have some random Pauli error, some random variable E, and the property that we have is that for any subset of qubits, the probability that all of these qubits are affected by the error is exponentially small in the number of these qubits. So there's a single parameter which characterizes the strength of this noise, so we will use this notation here. And the nice thing about this noise model is that these errors can be arbitrarily correlated. We're not assuming that we have IID noise on every qubit, for example. The other nice thing about this definition is that you can actually work with it. It's general, but not too general in some sense. So for example, we can analyze what happens when we have two errors that happen in succession. If they're both local stochastic errors, then the result of this product will still be a local stochastic error with an error rate which is just the sum. So this is true if these errors are independent, but in fact, we can also say something about the case where they are dependent. So this is combinatorics, basically. So suppose we have error rate P and Q, and we take the products, they're not necessarily independent, then we have this sort of upper bound on the noise strength of the product. So we'll call this effect error accumulation. The other property, of course, because we're talking about random Pauli errors, these errors are compatible with Cliffords. So if you have, for example, a depth 1 Clifford circuit and you conjugate the error by this Clifford circuit, then you know what, I mean, the support grows a little bit, but in a controlled way. And you can translate this into error rates, and you see that you pick up a square root. Okay, so this is error propagation. It means that we can propagate errors through a Clifford circuit forward in time and still control how the error grows. Okay, I will use this lemma in a bit, but right now, let me now define what I mean by a noisy execution of a circuit. So here's the formal definition, but it's easier if you just look at these pictures. So this is the ideal circuit that we would like to execute. And now a noisy implementation simply adds local stochastic errors at every stage. Okay, for example, after the preparation and after each gate and before the measurement. And let's assume for simplicity that we have a single parameter that this noise strength for each of these errors is the same. Again, I would like to emphasize that these errors, they can be correlated across qubits, but also in time, because this condition that these are local stochastic errors is just a statement about the marginal distribution. Okay, so now let's apply the lemma we had before. Let's assume we have a Clifford circuit. In that case, we can commute this Pauli error forward and use this error accumulation and push it forwards towards the end. And what we get is that this noise model is actually equivalent to a noise model, or we can estimate its property by considering this simplified noise model where we have an error that acts immediately before the measurement. Of course, this is only true for Clifford circuits, and it only makes sense if the circuit depth is not too large, because the dependence on the circuit depth is, of course, very bad. But we're only considering constant depth circuits. That's the good thing here. Okay, so let's go back to this problem of fault-tolerantly implementing a quantum advantage experiment. And the first idea you might have is, why don't we just apply the fault-tolerance threshold theorem? We can take an ideal circuit and we can recompile it into a larger fault-tolerant circuit that simulates the action of the ideal circuit as long as the noise is below some threshold noise rate. This is nice, but there's a slight problem with the current fault-tolerance constructions in that even if you start with a constant depth circuit, what you get here will not be a constant depth circuit. Okay? You blow up the circuit depth. At least we don't know how to analyze it in a way or give constructions that can be analyzed and that don't blow up the circuit depth. So we can't just plug in these standard constructions. Instead, we do something different. We take the problem and we sort of recompile the problem. We define a new problem, which I call the fault-tolerant problem. And this problem now has the property that it's still hard for classical constant depth circuits. And at the same time, you can solve it using a circuit which tolerates noise. Okay, so we don't actually solve the original problem, but we now solve a fault-tolerant problem. And we have a general transformation which takes a computational problem of a certain form, one that's defined in terms of classically controlled Clifford circuits, and turns it into such a fault-tolerant problem. So examples are this hidden linear function problem that we had initially, but also this embedded 1D magic square problem. Okay, so if you use this last problem, this embedded 1D magic square problem, then you can get the following result. So we now have a problem which you can solve with 99% probability, even if your implementation is noisy. And of course, this only holds if the noise rate is below some threshold noise rate P0 that we can compute. Furthermore, this quantum circuit only uses geometrically local gates in 3 dimensions. This is the case if we start with this 1D embedded magic square problem. It's not the case if you start with some other problem, as you will see from the construction. Okay, so this is essentially saying that this new problem can be solved even with noisy circuits. So now we have to make sure that they cannot be solved classically. So here, again, we have a circuit depth lower bound, which says essentially that you need circuit depth log n over log n to solve this problem classically. So in some sense, this hardness is preserved. We pick up some additional log n here, but this doesn't really change the picture. The bottom line is constant depth noisy quantum circuits are more powerful than ideal constant depth classical circuits. And here we only need 3D local gates. Okay, so in the remaining time, I would like to tell you a little bit, not about this transformation, because the transformation you will see is somewhat obvious, but about properties of the error correcting code we need. Basically, we need 3 specific properties, and all of these properties are satisfied by surface codes. So that's what our construction relies on. In principle, you could find other codes that have the same properties and instantiate this construction. Okay, so the first property is single-shot logical measurement, or just the fact that the code has an error threshold. And this is something well known. It just says that you can fault-tolerantly read out logical information. In particular, you can measure the logical Z operator fault-tolerantly. And the way you usually do this is you measure, say, every qubit in the Z basis. And if you didn't have any errors, then you would just take the parity of the bits on some string operator, say in the surface code, on this logical operator. But this will not be fault tolerant. What you want to do is you want to be able to tolerate noise. In this case, of course, this measurement results will be noisy. So you can't just take the parity, but you have to do some decoding. And then you can get this with high probability. So this works in the surface code. So the actual result here, I mean, this result is proven using standard techniques from Dennis et al. And also from Fowler. So what you can say is the following. You can get the parity, which corresponds to this logical observable, even from a noisy version of this measurement result. So E is the error, which we can assume is a Pauli X error. So we can get the correct result with high probability as long as the error rate is below 1%. And this is for the surface code. So even though this is a relatively standard construction, let me just show you how you define this decoding function in the case of surface codes. And just to make this clear, so we are interested in the expectation value, say, of this logical observable, which is the Z operator. We can choose this to be supported on this diagonal. And so in principle, we could just measure all the bits and take parity of the outcomes here. But if you have X errors, of course, this could lead to the wrong result, depending on whether or not you have an even or odd number of errors on this diagonal. So you don't, of course, know the errors, but what you can compute from the measurement results are the eigenvalues of the blockade operators, these blockade stabilizers. You see that these blockades will be unhappy. So then you can go to the dual lattice and do matching to get sort of a proxy for the actual error. This is going to be the assumption that the error is given by this one that you can obtain by minimal matching. And then you would, of course, in the decoding function, you would just take the parity along the diagonal and you correct for these parity switches wherever you have an error. So this would be the definition of the decoding function. And then to analyze this, you have to think about, again, what the actual error is. You have to combine these two effects. So you have the actual error and this proxy. And we have to think about what this has to do with the diagonal, whether we have an even or odd number of intersections with this diagonal. And then, you can formally write down this decoding condition that you decode correctly, and from this point on, it's just a matter of doing combinatorics and computing the probability that this doesn't occurs. Okay. So that's the first property. It's a single-shot measurement. The second property we need is the existence of transversal logical gates. How much time do I have? What time should I finish?
Well, after I finish, but then that's the questions at my 25.
Okay. Okay. Yes, thanks. So the first one is the logical measurements. The second one is Clifford gates, and in principle, it's enough to do protected gates, so you have to be able to do them with a constant depth circuit. And this is something we know in the surface code. Again, we can do Hadamard, X, Y, Z, and C naught gates if you restrict to constant depth implementations. But actually, we want more. We also want, for example, the S gate. And you can get this by just folding this code over. So you change the locality relations. This is a paper by Musa, and that shows how to do an S gate in this folded surface code. Okay, so the third requirement is, I think, the most interesting one. We need a procedure that creates logical states. And in principle, this means you want to be able to apply some ideal encoding unitary and get this logical state here. But we know that this can't be done in constant depth by Lieb-Robinson bounds. You need at least a depth which scales with the system size, even sort of polynomially. So the key point here is that we're not aiming for a logical state. This is impossible, but we are going to try to just create a logical state up to a Pauli correction, up to local stochastic errors. Okay. So this is what we're going to do. We're going to entangle the system with ancilla qubits, apply some shallow circuit, and then we can measure these ancilla qubits. We obtain some outcome S, and then this outcome should determine a Pauli correction, which maps you back to the logical state. Okay, so this can actually be done. So in the noise-free case, we want this shallow circuit to have this effect. So you prepare a logical state up to a Pauli correction, which you could in principle compute. In fact, we don't care about how efficiently you can compute this, because this part will be folded into the computational problem. Yeah, so we don't actually have to do this with the circuit. So this is what you want to achieve in the noise-free case. In the noisy case, we might have errors inside the circuit. We can commute them forward. And basically what we want to do is we want to understand the effect of errors at this stage. Okay? And as you see here, these errors that act on the system, we don't get any syndrome information from these ancilla measurements. So we cannot expect to get rid of all errors. There will be something left, even if you choose the right recovery function. So this might take into account these errors, but there will be some residual error that depends on this error here. So we call this the repair function. You should think of it as the residual error if you run this circuit. And now the combinatorial property that we want is we want to be able to say something about this residual error if we know the noise rate of this error here. So we want to be able to say that if you have local stochastic errors with rate p here, then this is equivalent to having a local stochastic error here with a related noise rate, which has this functional dependence. And this we can do for the surface codes to get some bound that looks not so nice, but the main point here is that it's still local stochastic and we have control over the error rate. Now, I don't have too much time left, but what I would like to do is I would like to explain at least the definition of this recovery and the repair function. And then after that, it's sort of a lot of combinatories to establish this bound. But first I have to actually tell you what the construction is. So we start with this beautiful paper from Brausendorf, Rabi, and Harrington, where they look at long-range localizable attenuation in the 3D cluster state. And essentially that gives you a procedure. What they're saying is you should start with this 3D cluster state and you measure all the red and black qubits using single qubit measurement. And then what you end up with on the surface, these yellow qubits, will be a belt state encoded in 2 surface codes. And this is true up to Pauli correction. The Pauli correction is determined by the measurement outcomes you got in the bulk from these red and black qubits. And in fact, I should say that in this paper, they already analyzed the effects of noise in the bulk qubits. But because they were interested in long-range localizable entanglement, they sort of considered ideal operations on the boundaries. So the only extension, in some sense, that we make is we use this more general notion of local stochastic errors, and we can say something about noise everywhere. Okay, so let me briefly explain what kind of information you get when you measure these qubits. As I said, basically, you can determine what the logical eigenvalues are for these surface codes. So this depends on the measurement outcomes S in the bulk, and you also know something about the stabilizers of the surface codes. So this is in the case where you have no errors. And what's important is that somehow the measurement outcomes in the bulk are not independent, but there are lots of constraints. They come from a Z2 gauge model, a classical code in some sense. And this part you can use to deal with errors. So if you have errors, then you can actually use this information to determine the homology class of the error. And it turns out that these eigenvalues only depend on the homology class. So that's why you can decode in some sense. Okay, so here's a caricature of the situation. So we have the bulk, we get this measurement outcomes S. And as I said, we can determine the eigenvalues of the stabilizer operators of the surface code on the boundary. I'm only showing you one boundary. So then the first thing you might try is you might say, well, the recovery function should just match these up. So we should do minimal matching to get rid of these excitations. Unfortunately, this doesn't quite work because we might have errors. And what happens with errors is you get additional excitations in the surface codes here and here that correspond to endpoints of these errors. And these are not observable. So the important thing here is that the syndrome caused by the error, we cannot observe it because we're not measuring the stabilizers of the surface codes. We're only doing single qubit measurements in the bulk. Okay? So we know about these excitations, we don't know about these. In principle, we want to match up all of them. So we should find a recovery map that does this, but we don't know the error, and we don't know the syndrome caused by the error on the surface code. So then what we do is basically we again use a proxy for the actual error. And in fact, what we know about the error is the syndrome caused in the bulk. Okay? So we know that we see the endpoints of these errors in the bulk. And now we just use a minimal weight error that is consistent with this syndrome. Okay? That's something like this. And we just use this as instead of the error. And then we can define the recovery operation as matching up the defects that we have originally and the ones caused by this proxy of the error. And so this isn't quite correct. If you look at this, we didn't do the right thing because we have the proxy instead of the actual error. But we still have this degree of freedom, this repair function that we can choose, and we're just going to choose one that is consistent with this difference. So it takes care of this discrepancy, and it's chosen as a minimal weight matching that satisfies this. Okay, so I have 2 more minutes, so I would like to put everything together now. So we start with the surface code, single-shot preparation, but of course we don't want the surface code, we want the folded surface code, so we should fold this. Then everything is local. This took me a while, as you can imagine. So in this way we can prepare encoded, folded surface code belt states, and then we can just play this embedded one magic square game using these encoded states and use these transversal operations that you have between nearest neighbor. Okay, so there are a few open problems. I think one of the most interesting one is the question of whether you can do this in 2 dimensions instead of 3 dimensions. I guess, yeah, seems to be a difficult problem, but so I'm interested in any ideas you might have. Then I think it will be interesting to find sort of converse results that say if the noise rate is too high, then things become easy classically. And in fact, in the noiseless case, there's a recent result by Daocheng Wang, which shows that this HLF problem that I mentioned initially can be solved with only log n squared depth. Okay, so you can't solve it with log n, but you can solve it with log n squared. And maybe one could try to see how this changes as you increase the noise level. Okay, so that's, well, thank you.
So, any questions for Robert? Oh, wait for the mic, hang on.
You're using some classical compute here also for the error correction. How does the classical work depth here of the error correction scale?
Oh, so you're referring to the recovery function and so on, which includes minimal matching, which has like n cubed runtime. So that part we don't actually have to build into the circuit. Okay? So I didn't show you this construction, but everything that is related to error correction, to classical decoding, is put into the relation, okay? Into the problem. So this is only something that you have to compute if you want to verify that your quantum circuit produced the right result. But the quantum circuit itself doesn't have to compute this. So we don't have to actually ask this question. And in fact, it will scale with the system size. It will not be constant size.
For Dan, that's a good question, because I was going to ask exactly the same one.
Thanks, Robert. Could we go back a few slides to the sort of the schematic, that one? So in the full scheme, there seems to be a combination of this 3D cluster state error correction and sort of entanglement swapping between layers. But in some sense, there's a lot of similarities between the way you teleport data through a cluster state and entanglement swapping.
Yes.
So is it important, I mean, the width of these wedges versus the number of these wedges, is there an important trade-off there? Or could they all be seen as just one big wedge?
Yes, that's a very good question. Actually, I mean, the way we started thinking about it was in terms of one big wedge. creating long-range entanglement. But actually, I mean, what we're doing here is we're encoding every qubit into a single code, basically. And the advantage here is that everything remains local, in particular in the analysis of the classical hardness. You still have the same locality relation as in the unencoded problem. Whereas if you stretch it out, then you have to analyze whether the error correction in this whole cluster state somehow makes the classical problem easier.
So you need that identification to individual classical bits,
Yes.
the layers to be.
So this makes the analysis very simple. I mean, I don't know whether it's true or how to show it.
Thank you.
It's great.
Okay, let's thank Rob. Oh, one more question, if it's a quick one.
So when you explain the circuit error model, you say the error happening in each layer or time steps is equivalent to the error right before the measurement. Is it true for any circuit with Clifford gates only? Do you have any other constraints?
I mean, here we use Clifford gates, and the gates have to be, I mean, they have to be 2 local or 1 local. Otherwise, the support would grow. You shouldn't use a 10 qubit gate or so.
So your error
Then the
model
bands will be slightly different. But
yeah, your error model has a single parameter p. Does that apply to all single qubit gates and the single gate?
we use the same parameter p, but in principle, you could use different p's. And you just have to sort of combine the errors properly using this level. So we don't necessarily need the same error rate for every gate, but that's just a simplifying assumption here.
Okay, let's thank Robert again for his talk.